Hello everyone, today we're going to be looking at Quantipus number 18, which is another brain teaser, and for this one you have to kind of come up with a solution that's pretty outside the box. Basically, we have 4 identical light switches outside of a closed room, and they're all initially off, and then inside the room we have a single light bulb, and exactly one of the switches outside controls it. So you're free to flip any switches as many times as you like before entering, and it's asking us what is the minimum number of times you must enter the room to be certain which switch operates the bulb. Alright, just to illustrate this, I have a little drawing. I know my light bulb is not very good, but this is supposed to be a light bulb over here, and then these are your 4 light switches outside of the room. So let's just label them 1 through 4. So this will be switch 1, 2, 3, and 4. Now we can certainly approach this like we have a bunch of problems before, where we're trying to optimize to find the minimum number of something, and that's just basically going to require us to maximize the amount of information that we can gain on each trip into the room. So what information do we have upon entering? Well, we can basically observe the light bulb and see if it's on or off. So I'll call this on question mark. And this is essentially a binary indicator where we can say it's 1 if we see that the light's on, and it's 0 if we see that the light is off. Well, this is essentially a single bit which has 2 states, 0 and 1. So that means that we can distinguish between 2 different groups per trip into the room. So given I can only look this one bit, how would I actually employ this strategy? Well, basically I can split my switches into 2 different groups. I'll call this group 0, and then I'll call this group 1. And then what we can do is basically flip both of these switches to the on position, both 3 and 4. Then if we go into the room and we see that the light's off, so this will be a 0, we basically know that the switch that controls the light bulb is going to be in group 0. And if instead the light switch was on, then we know that the switch that controls it will be in this group. Now, once I know which group of 2 it's in, I could essentially eliminate 2 of these options, and now we're left in a situation where we have 2 switches. So what I can do is just flip one on and one off and go into the room, see if it's on or not, and that will dictate which is my switch. So if all the information we have is the switch on or not, well then that's going to take us 2 trips into the room, but is there any way for us to do better? Now this is where the BS kind of kicks in, where the thinking outside the box comes in, is that we can add more information by feeling the heat of this light bulb. So once I enter the room, I can also go up to the light bulb to feel how hot it is. So essentially we're adding another bit of information. Let's call it hot question mark. Now, since I essentially have 2 binary indicators, 2 bits of information, that allows me to distinguish between 4 groups, right? I have 4 different states in 2 bits. Therefore now, since I have 4 switches, I should be able to come up with a strategy such that it only takes me 1 trip to find the switch. Now, how would I actually come up with the strategy? Well, there's a pretty simple process to doing so. Let's just assign each of these switches to an output from our 2 bits, right? So we can say this one's 0, 0, this one's 0, 1, this one's 1, 0, and this one's 1, 1. Also, you might ask, aren't these bits just kind of telling me the exact same piece of information? If the switch is on, well, then it's also going to be hot, and if it's off, then it probably won't, which is true, but the way we can make this 2 different pieces of information is by waiting a certain amount of time, right? So let's just draw a timeline. I'll call this point X and I'll call this point Y, and then there's just going to be some time interval in between them. And this is just a time interval such that if I turn on the bulb here and then I turn it off here, it's going to still be hot. So now, since this is how we decided to distribute the binary information for these 4 switches, I'm essentially going to take this bit, the second one, which represents the hotness level of the bulb, and I'm going to take 2 and 4 and I'm going to turn them on at point X. So I turn on 2 and 4 here, and essentially I want to enter the room right here, or just like very shortly after point Y. Therefore, since the leftmost bit is controlling the on level, I want at point Y all the switches with a 1 here to be switched on, and all the switches with a 0 to not be switched on. So how do I make that happen? Well, I turned on switch 2 over here, but I want it to be off at point Y, so I turn off 2, and then I'm going to turn on 3, right? So I turn off 2 and turn on 3, and this just makes it such that when we enter the room right here and we observe our 2 bits, they're going to exactly correspond to which light switch is the one that controls the light. So for example, say that I entered and I saw that the light switch was off and I felt that it was hot. Well, 0, 1 corresponds to switch number 2, so we know it's going to be switch number 2, and that makes sense because we turned on switch 2 a long time ago and then we waited and we turned it off. So that means it's going to be off and hot. If it was off and not hot, well then we know it was bulb number 1 because we never turned it on ever. If instead it was on but not hot, well then we know it's switch number 3 because we just turned it on before we entered the room, so it shouldn't be hot and it should be on. And then if it was both on and hot, well then we would know it's switch number 4 because we had it on back here and we never turned it off, right? So therefore, using the strategy, it's only going to take us one trip into the room, and that's the best that we're going to be able to do.